Particles at the quantum scale behave in ways that challenge every assumption we make from living in the everyday world, and understanding this difference is the first step to realizing why they can sometimes pass through walls. When we look around us, everything seems solid, predictable, and fixed in place. A wall stops a ball, a door blocks sound, and objects cannot simply appear on the other side of a barrier. But this familiar behavior comes from the world we interact with, a world made of countless particles that follow classical physics. When we zoom in far enough, however, the rules change dramatically. Quantum particles, such as electrons, protons, or even atoms under certain conditions, do not act like miniature versions of the objects we see. They behave according to the strange laws of quantum mechanics, where probability, wave-like behavior, and uncertainty dominate. This means a particle does not exist at a precise point in space until it is measured. Instead, it exists in a spread-out cloud of possible locations, each with a certain probability. This wave, like nature, is crucial to understanding why particles can behave so differently from everyday objects. Instead of moving in a straight, predictable line, a particle's existence stretches, oscillates, and shifts through space. This gives the particle the ability to interact with obstacles in a way that defies our intuition. In the quantum world, a barrier is not an absolute stop sign. It's more like a region where the particle's probability becomes weaker. Some of the particle's wave can penetrate the barrier, and while it weakens rapidly, there is still a small chance it can appear on the other side. This is something no object in the classical world could ever do. The particle is not breaking the wall. It is simply following quantum rules that allow its presence to spread beyond limits imposed by classical boundaries. When scientists study these tiny particles, they often observe them behaving in ways that seem random or unpredictable. But these behaviors are not chaos. They follow deep mathematical patterns that describe how a particle's probability wave evolves. The strangeness arises because quantum behavior cannot be explained using the logic of the macroscopic world. A particle is not just a point, it is a wave of possibilities. It does not travel through space in a continuous line. It shifts and reshapes based on interactions and probabilities. This is why particles can do things like pass through barriers, teleport between quantum states, or exist in multiple possible states at once. These effects are not visible to us because they only occur at the tiniest scales, far smaller than anything we can see with the naked eye. In documentary terms, the quantum world is an unseen realm where the rules of existence are rewritten. It is a place where particles are not bound by the same restrictions as solid objects, where movement is not simply physical but probabilistic, and where the building blocks of reality follow a language unlike anything we experience in daily life. Understanding this foundational difference is essential because it explains how particles can perform seemingly impossible feats. The hidden ability of particles begins with their quantum identity, a form of existence that allows them to move, interact, and appear in ways that defy all classical expectations. Quantum tunneling is one of the most mysterious and captivating abilities in the microscopic world, a phenomenon that allows particles to pass through barriers that, according to classical physics, should be completely impossible to cross. To understand tunneling, we must step away from the rules we see in everyday life. In our world, if something doesn't have enough energy to climb over a hill, it simply cannot get to the other side. A car without enough power cannot climb a steep slope, and a thrown ball cannot pass through a wall unless it breaks it. But on the quantum scale, particles do not follow this predictable logic. They behave as both particles and waves, and this wave, like nature, changes everything. A particle approaching a barrier does not stand before it like a tiny solid object. Instead, Its existence spreads out like a wave that naturally seeps into and beyond the barrier. The wave weakens quickly, but it never becomes zero. This means there is always a small chance that the particle will appear on the other side. Quantum tunneling happens because a particle is never confined to a single point. It exists as a cloud of probabilities, and this cloud can leak through a barrier even when the particle does not have the energy to cross it in the classical sense. When this probability leaks far enough, the particle can suddenly be detected on the other side, as if it has slipped through solid matter. It has not broken the wall or forced its way through. Instead, it has followed the mathematics of quantum mechanics, which allows its wave function to extend into forbidden regions. Scientists describe this as the particle borrowing, the possibility of existing beyond a boundary, a possibility that no classical object could ever possess. This effect is not rare or exotic. It is happening constantly throughout the universe. Tunneling is the reason the sun shines, because particles inside the sun use tunneling to fuse together, even when they don't have enough energy to collide naturally. It is the principle behind many modern technologies, including the components in smartphones and computers that rely on tunneling to control electrical signals on unimaginably small scales. It even plays a role inside atoms, helping particles shift positions and allowing chemical reactions to occur. What makes tunneling so astonishing is that it demonstrates how deeply different the quantum world is from the macroscopic world we see. In a documentary sense, quantum tunneling shows us that nature has hidden pathways, routes that bypass the normal limitations of energy and motion. To the human mind, it seems impossible for something to cross a barrier without breaking it. Yet this is precisely what particles do billions of times every second. The universe at its core operates through probabilities and wave-like behaviors, enabling particles to perform feats that defy logic. Tunneling is not a trick. It is a fundamental rule of the quantum world, revealing that the smallest pieces of reality move through existence in ways far stranger and far more elegant than anything we experience on the surface. Light holds a unique place in the universe because it behaves as both a wave and a particle, yet its ability to move through different materials depends entirely on its energy, wavelength, and how it interacts with the matter around it. When we think of light, we imagine brightness, speed, and the effortless way it crosses empty space. But the moment light reaches a solid object, its behavior changes dramatically. Unlike quantum particles that can sometimes slip through solid barriers, light is deeply affected by the arrangement of atoms and electrons within the material it encounters. The reason light cannot pass through a wall in the same way particles can is not because it lacks energy or power, but because its wave-like structure interacts strongly with the electrons locked inside the atoms that make up the wall. These electrons respond quickly to incoming light, absorbing or scattering its energy, which prevents the light from continuing forward. In the quantum world, every form of energy comes with specific characteristics, and for light, those characteristics are determined by its wavelength. Light with longer wavelengths, such as radio waves, can pass through walls with ease because their waves are large compared to the tiny spaces within the atoms. But visible light, the kind our eyes can detect, has much shorter wavelengths. These short waves interact intensely with the electrons in the wall, causing those electrons to vibrate and absorb the energy rather than allow it to pass through. This is why walls appear opaque. The electrons trap the light and instantly convert its energy into heat or scatter it in different directions. In contrast, transparent materials such as glass or water have atomic structures that allow light waves to move through without being caught or scattered, which is why we can see through them effortlessly. Light's behavior also reveals an important truth. Being both a particle and a wave does not give it the same freedom as quantum particles like electrons. While electrons possess mass and a wave-like probability field that allows them to tunnel through barriers, light does not have this kind of probabilistic spread when interacting with dense matter. Its wave must obey the rules set by the material. If the atoms allow the wave to pass, light moves forward. If the atoms block the wave, light is stopped instantly. The reason comes down to electromagnetic interactions, the fundamental forces that dictate how light couples with charged particles. These interactions are strong inside a solid wall, leaving no room for light to tunnel through under normal circumstances. In a documentary sense, light is a traveler whose journey is shaped by the invisible architecture of matter. It glides freely through the vacuum of space, bends through air and water, and reflects off surfaces that capture its energy. But when it meets a solid barrier, it faces a dense landscape of electrons that act like sentinels, absorbing or redirecting any wave that tries to pass. Light's dual nature does not grant it the ability to cross solid objects the way quantum particles sometimes do. Instead, it reveals how delicately light is woven into the fabric of matter, responding to each atom and each electron with absolute precision. This interaction explains why the world appears solid and visible, because every surface around us is constantly shaping, stopping, and transforming the light that strikes it. The probability-based nature of quantum mechanics is one of the most fascinating aspects of the microscopic world, and it plays a central role in explaining how particles can cross barriers that should stop them completely. In everyday life, events follow clear and predictable rules. If you throw a ball at a wall, it will bounce back every single time. If a car does not have enough power to climb a hill, it will roll backward, not magically appear at the top. But in the quantum world, certainty is replaced by probability. Particles like electrons, protons, and even atoms behave according to mathematical waves of chance. Instead of having one fixed position, they exist in a spread of possible positions. Instead of traveling on a single path, they explore many potential paths at once. This shift from certainty to probability is what makes quantum mechanics so strange, and yet it is the foundation that allows particles to perform the seemingly impossible. When a particle approaches a barrier, classical physics says it cannot pass if it lacks the required energy. But in quantum mechanics, the particle's wave function, the mathematical description of all its possible locations, extends beyond the barrier. The wave does not suddenly stop at the wall. It gradually weakens, becoming smaller and smaller, but it continues to exist on the other side. This means there is always a chance, however tiny, that the particle will be found beyond the barrier if we look for it. The particle does not force its way through the wall. It simply follows the rules of probability that govern its behavior. Sometimes the likely outcome happens and the particle bounces back, but in rare cases, the unlikely outcome occurs and the particle appears on the opposite side. This is what physicists call quantum tunneling, and it is a natural result of the probabilistic nature of the quantum world. What makes this phenomenon even more incredible is that it is not random in the chaotic sense. The probabilities follow precise mathematical laws that have been tested and proven through countless experiments. The behavior is predictable in terms of likelihood, but not in terms of guaranteed outcomes. It is like rolling a die billions of times. Each roll is uncertain, but the pattern of results follows clear rules. Quantum particles are constantly rolling the dice of probability as they interact with their surroundings. And every interaction is a blend of possibilities that may or may not become reality. In a documentary sense, the quantum world becomes a place of endless potential. Instead of solid walls and rigid boundaries, it is filled with barriers that particles can sometimes pass through because the universe leaves room for unlikely events to happen. Reality at this scale is fluid, flexible, and governed by chance rather than certainty. The idea that a particle might appear on the other side of a wall is not a violation of physics. It is an expression of the deeper rules that shape the structure of the universe. Probability is the language of the quantum world, and understanding this language reveals a hidden dimension where particles navigate through possibilities that our everyday intuition could never. Imagine, in the quantum world, the idea of an electron cloud shows us just how different the smallest pieces of reality are from the objects we experience every day. When we think of an electron, it is tempting to imagine a tiny ball orbiting the nucleus of an atom like a planet circles the sun. But this picture is completely inaccurate. In truth, an electron does not move in a predictable path or stay in one exact location. Instead, it exists as a cloud, a region of space where the electron is likely to be found. This cloud is shaped by the electron's wave function, a mathematical description of its probability of appearing in different places. Rather than being a solid particle, the electron behaves like a spread-out wave that occupies multiple positions at once. This strange and beautiful feature lies at the heart of quantum mechanics and reveals why particles at this scale can behave in ways that appear impossible to us. The electron cloud is not just a metaphor, it is a measurable reality. Scientists have observed patterns formed by electrons that show these clouds truly exist. Inside an atom, electrons do not orbit, they occupy orbitals, shapes that represent regions where their presence is most likely. These shapes can look like spheres, dumbbells, or even more complex forms, depending on the electron's energy. This means the electron is not tied to a single spot, but is smeared out over space, living in a state of possibility. This spread-out nature helps explain phenomena like quantum tunneling, because if an electron is not confined to a point, parts of its wave can reach into areas that classical physics would consider forbidden. The electron cloud itself is a living example of how probability defines the structure of reality at the smallest scales. This cloud, like existence, also reveals a deeper truth about matter. What we think of as solid and stable is actually built from particles that are never truly still or localized. The walls around us, our bodies, and every object we touch are made from atoms whose electrons are dancing in probabilistic clouds. These clouds form the structure and shape of matter, determining how atoms bond, how energy moves, and how everything interacts. Even though atoms seem solid, most of the space within them is empty, filled only with these electron clouds that define where the electron might be. This means the solidity we feel is not due to fixed particles, but due to the interactions between these probability clouds. In a documentary sense, the electron cloud transforms our understanding of the universe. It shows that reality is not made of tiny, predictable beads of matter, but of waves of possibility, constantly shifting and spreading. The electron cloud paints a picture of a world where certainty dissolves into probability, where particles exist as shimmering patterns of potential. This is not chaotic or random. It is governed by some of the most precise laws ever discovered. The electron cloud is a window into the hidden layer of existence, revealing that the foundation of everything we know is built from shapes of probability rather than solid, unmoving particles. By understanding this, we begin to grasp why the quantum world operates with such flexibility and how particles can accomplish feats that seem impossible in the world we live in. When light encounters a solid wall, its journey ends almost instantly because the electrons inside the material absorb, scatter, or reflect its energy before it can move any farther. To understand this, we must imagine the wall not as a rigid block, but as a dense network of atoms, each surrounded by constantly moving electrons. These electrons respond to incoming light with extraordinary sensitivity. Light is an electromagnetic wave, meaning it is made of oscillating electric and magnetic fields. When these fields hit the electrons in a wall, the electrons start vibrating in response. This vibration quickly absorbs the energy of the light wave, preventing it from continuing through the material. The light does not have a chance to slip through or hide between atoms because the electrons are constantly interacting with it. This strong interaction explains why walls appear opaque. They simply do not allow visible light to move past their tightly packed atomic structure. This behavior is different from what happens with transparent materials such as glass or clear water. In those materials, the atoms are arranged in a way that allows light waves to continue through without being absorbed. The electrons in those substances vibrate in a manner that does not trap the energy of visible light, allowing it to pass through. But in opaque, solid materials like wood, concrete, or stone, the electrons absorb the energy almost immediately. The light is effectively stopped at the surface, turned into heat or scattered in many directions. This is why we can see walls and why they block our view of what lies behind them. Light interacts strongly with matter, and this interaction determines whether something is transparent, translucent, or completely opaque. What makes this contrast so remarkable is that light is incredibly fast and carries significant energy, yet it is still stopped by ordinary matter. While quantum particles such as electrons can sometimes tunnel through barriers due to their probability-based wave nature, light is constrained by the electromagnetic properties of the material it strikes. It cannot tunnel through walls under normal circumstances because the interaction between its wave and the electrons in the material is too strong. The moment the light hits the wall, its wave is disrupted, the energy is absorbed or bounced back, leaving nothing to continue forward on the other side. This explains why the sun cannot shine through concrete and why shadows exist as clear boundaries of blocked light. In a documentary sense, this phenomenon reveals how the universe is shaped by invisible interactions. Light travels effortlessly through the vast emptiness of space, crossing millions of kilometers without losing strength, but a thin wall of painted brick stops it instantly. The atoms in the wall form a defensive barrier, each electron acting like a guardian that captures or scatters the light. This constant dance between light waves and electrons determines what we see and what remains hidden. Every beam of light that hits a surface becomes part of this invisible battle, a struggle dictated by the laws of electromagnetism. Light's inability to pass through walls is not a weakness. It is a natural consequence of how deeply it is connected to the charged particles that make up the matter around us. Particles with extremely small mass and strong quantum uncertainty have an unusual ability to leak through barriers under conditions where ordinary matter would be completely stopped. This ability is rooted in the delicate, wave-like nature of particles at the quantum scale. Unlike objects in the everyday world, a quantum particle does not remain fixed in one exact position. Instead, it exists in a blur of possibilities, spreading over space like a gentle, fading ripple. When this ripple encounters a barrier, it does not halt abruptly the way a solid object would. Instead, part of the particle's wave slips inside the barrier and weakens as it moves through. Sometimes the wave weakens too quickly, and the particle is found back on the original side. But occasionally, the wave stretches just far enough for the particle to appear on the far side of the barrier. This sudden appearance is not a trick. It is the result of quantum laws that allow particles with very small mass to move in ways that classical objects never could. The key lies in the relationship between mass and uncertainty. Particles with tiny mass, such as electrons, have very high quantum uncertainty. This uncertainty makes their wave functions spread much farther, meaning their presence is less localized and more flexible. Because they are not pinned down to a single location, they can explore regions that classical physics defines as forbidden. Their wave, like nature, gives them access to hidden pathways that lie beneath the surface of the physical world. Heavier objects like protons, atoms, or molecules still have wave functions, but these waves are much more confined. Their probability clouds do not extend far enough to give them the same freedom. This is why tunneling becomes rare and eventually disappears as mass increases. The universe allows only the smallest particles to slip through barriers because only they have the quantum uncertainty needed to stretch across them. This fragile balance between mass, uncertainty, and probability is constantly at work in nature. Inside stars, lightweight particles tunnel through energy barriers to fuel nuclear reactions. Inside electronic devices, electrons tunnel through tiny gaps to create the signals that power phones and computers. Even in chemical reactions within the human body, small particles sometimes tunnel to trigger processes that make life possible. These events happen at scales far too small for the human eye to detect, yet they shape everything we see in the world around us. In a documentary sense, this phenomenon paints a picture of the universe as a place where the smallest particles dance along the edge of impossibility. Their tiny mass grants them a flexibility that lets them slip through cracks in reality that larger objects cannot enter. It is a hidden ability operating quietly behind the scenes, revealing that even the simplest particles are capable of extraordinary feats when guided by the laws of quantum uncertainty. Understanding the fundamental differences between quantum particles and light opens a window into how nature operates beyond human perception and reveals why the rules that govern the microscopic world are so unlike those we experience in daily life. The universe, at its core, is built on principles that often defy intuition. Solid walls, opaque objects, and seemingly impenetrable barriers dominate our macroscopic experience, leading us to believe that nothing can pass through them without force or destruction. Yet, at the quantum scale, reality behaves differently. Particles, guided by the rules of probability and quantum mechanics, can sometimes appear on the other side of barriers, while light, despite its speed and energy, is stopped by the electrons within matter. This contrast highlights a profound truth. The universe operates under different sets of laws depending on scale, and what is possible at the microscopic level may seem impossible to our senses. The key difference lies in how quantum particles and light interact with matter. Quantum particles, such as electrons, possess mass, uncertainty, and wave-like properties that allow their probability clouds to extend into forbidden regions. Even when classical physics predicts they should be trapped, these particles can tunnel through barriers, appearing on the other side without breaking or passing over the obstacle in a conventional sense. Light, on the other hand, interacts with the electromagnetic fields of electrons in a solid. When it strikes a dense material, its wave is absorbed or scattered, leaving it unable to move forward. The difference is not about strength or speed. It is about how nature has programmed different forms of energy to respond to matter. Quantum particles exploit probability and uncertainty, while light obeys the rules of electromagnetic interaction. This distinction also emphasizes how much of reality exists beyond the reach of human perception. We see the world as solid and predictable, but beneath the surface, particles move in waves of probability, slipping through spaces that appear impenetrable. Every atom, every electron, every tiny quantum particle is governed by these hidden laws. Observing their behavior allows scientists to understand processes that power the sun, fuel electronics, and enable life itself. The interplay between what we perceive and what occurs at the microscopic scale demonstrates that reality is multi-layered, and that our everyday intuition only scratches the surface of how the universe truly operates. In a documentary sense, these differences invite us to reconsider the nature of existence. The world we touch and see is only one layer, visible because of the way light interacts with matter. Beneath it lies a hidden realm where particles navigate barriers effortlessly, where probability shapes behavior, and where the ordinary rules of physics are rewritten. Recognizing these differences expands our understanding of nature, showing that the universe is far stranger, more elegant, and more mysterious than the surface reality suggests. By exploring these hidden rules, we gain insight into the delicate balance that allows both matter and energy to exist, interact, and create the world as we know it, while also revealing the astonishing freedom and hidden abilities of particles at the quantum scale.